Lesson 8.3, we're going to continue to talk about some hypothesis testing. This time we're going to talk about the chi-squared goodness of fit test. So this is different than the chi-squared test for independence, which we looked at last time. The test for independence looks at two different variables, like gender versus music preference, and compares them to decide whether they're related or not. For the goodness of fit test, we're looking at one variable and deciding whether that data satisfies a certain probability distribution. Next chapter, when we get into probability, we'll be talking about different types of probability distributions, and we'll be able to expand on this. This chapter, since we haven't talked about that yet, I'm giving you one probability distribution here, the uniform distribution. Anything else, I'll give you the frequencies that you need until we learn how to find the frequencies next chapter. So the one I'm going to give you right now is the uniform distribution, which just means that everything's the same. So no matter what outcome you're looking at, you would expect it to be just exactly the same as any other outcome in your event. The chi-squared goodness of fit test, like I just said, it measures how closely the observed data fits the expected data for whatever you would expect that distribution to be. So how well does this data fit a uniform distribution? The way that we calculate degrees of freedom, since there's only one variable for a goodness of fit test, it's just how many ever possible outcomes there are minus 1. And your null and alternative hypotheses, your null hypothesis is there is no difference, so you're saying that the data does satisfy whatever distribution you're looking at, and your alternative hypothesis, there is a difference, it does not satisfy the distribution that you're looking at. So here's an example. The students in year 8 are asked what day of the week their birthdays are in this year, and the table shows our results here. So we want to find the expected values. For birthdays, we assume that every day is just as likely as any other day to be born. So that's going to be a uniform distribution. So we want to find the expected values, how many we would expect to be on every day. Since we're assuming or testing this against a uniform distribution, we would expect them all to be the same. So figure out how many you would expect to be on every day of the week given the number of responders. So since this is a uniform distribution, we're assuming that every day is equally as likely as any other day. So I just counted up how many total responders there were. There was 105 total responders. Every day is just as likely, so divide it by the 7 days of the week. So every day we would expect there to be 15 birthdays. So now we want to conduct a chi-squared goodness of fit test at the 5% significance level. So that means that alpha is 0.05. So go ahead and pause the video and do parts I and double I. Write down your null and alternative hypotheses for this uniform distribution, and then find your number of degrees of freedom. So whenever you're doing a goodness of fit test, it's always your null hypothesis is that the data does satisfy whatever distribution you're looking at. So in this case, we're looking at a uniform distribution. And then your alternative hypothesis is that the data doesn't satisfy a uniform distribution. For your number of degrees of freedom, since there's only one variable, your amount of variability is just how many ever possible outcomes there are minus 1. So 7 minus 1, your number of degrees of freedom is 6. So now we want to find our chi-squared test statistic and our p-value. So this is different from the test for independence because this is now the goodness of fit test. So the way you're going to do this is you're going to go into your two lists. So you're going to go to stat edit, and you're going to edit your two lists just like if we were doing like two variable stats. List 1 is your observed values, so the ones that they actually found here. And then list 2 is going to be your expected values. So in this case, it's just 15 for all 7 of them. Then you're going to go back into stat, go to tests, and now we're going to go to D, which is the chi-squared GOF, goodness of fit test. And once you go in there, make sure your observed is listed as L1, your expected is listed as L2, and you have to insert the number of degrees of freedom, which we just found here in part 2, so that's 6. So go ahead and pause the video and try that and see if you can come up with the chi-squared test statistic and the p-value. So using your graphing calculator, you should have found that your chi-squared value was 1.6 and your p-value is 0.953. I'll show you guys again how to do this in class as well. But using those two values, now part C, they tell us our critical value, which remember always has to either be given, or if you're doing it by hand, you have to read it off a table. So given this critical value, they also gave us our alpha level up here. Write down the conclusion. So are we going to accept or reject our null hypothesis? And those rules, accepting and rejecting, are exactly the same as the chi-squared test for independence. So go ahead and pause the video and come up with a conclusion for this test. So using the same rules that we had from section 8.2, we have our chi-squared value is 1.6, which is smaller than our critical value, 12.592. Or you can look at the p-value compared to the alpha level. So the p-value is 0.953, and that's greater than the alpha level of 0.05. So because your p-value is greater than your alpha, we do not reject our null hypothesis, or IB accepts, we accept our null hypothesis. So basically what that means is that our data satisfies a uniform distribution. With the information given, we can assume that it's close enough to a uniform distribution. So this is basically saying that the probability of this data being a uniform distribution is 95%. So that's pretty high. So scores for an IQ test are normally distributed with a mean of 100 and a standard deviation of 10. Next chapter, we're going to be talking about normal distributions and how to find them and how to calculate them and all of that. So Cynthia gives an IQ test to all 200 IB diploma program students at our school, and the results are given. Normally, you would just be given the observed frequencies here, and you would have to calculate your expected frequencies. But because we haven't actually studied normal distributions yet, I gave you the expected frequencies based on this normal distribution information. After next chapter, you'll be able to find these on your own. So she wants to test whether or not these results are normally distributed as well, and she performs a chi-squared goodness of fit test at the 10% significance level. So first thing, go ahead and pause the video and write down your null and alternative hypotheses. So same wording as the way before, the data satisfies a normal distribution. In this case, we're going to be a little bit more specific. Again, this will make more sense after we talk about normal distributions, but satisfies a normal distribution with a mean of 100 and a standard deviation of 10. And then your alternative hypothesis, the data does not satisfy this normal distribution. Whenever you're doing any type of chi-squared test, whether the test for independence or the goodness of fit test, you always need to have your expected values to be at least 5. If it's smaller than 5, there's not enough data in that category to correctly do the test. So we always need to make sure our expected frequencies are always at least 5. So if we look at our table over here, these bottom two categories are smaller than 5. So we need to combine some groups to make sure that every expected frequency is at least 5. So in order to ensure that all the expected frequencies were over 5, since these first three categories were all good, I just left them the same. I originally looked at just combining these bottom two, but they would still have an expected frequency of below 5. So I ended up combining all three of these bottom categories, these bottom rows together, and created a row that was all x's greater than or equal to 110. So instead of having all three of these rows, I now just have this one row here, where the observed frequency, I added all three of these together, and the observed frequency was 107. And then the expected frequency, add all these up, and you end up with the expected frequency to be 31.75. So when I go to do my chi-squared goodness of fit test, I'm going to only have 4 rows. The first 3 are going to stay the same, and then my 4th row is going to be this one down here. So now that we've updated our table, go ahead and do parts C and D. So calculate the number of degrees of freedom and then actually do your chi-squared goodness of fit test. Find your chi-squared test statistic, the p-value, and state your conclusion. So for part C, number of degrees of freedom, since we combine these 3 rows together, we only have 4 rows. The x is less than 90, 90 to 100, 100 to 110, and then greater than 110. So our degrees of freedom are 4 minus 1, which is 3. And then using my graphing calculator, I went into stat. List 1 is our observed frequencies, again combining these 3 together to make it 107. List 2 is our expected frequencies, combining these 3 together to get 31.75. And then I went into stat, test, goodness of fit, chi-squared goodness of fit. So then we had, once I did that, I got that our chi-squared value was 244. And our p-value was 1.02 times 10 to the negative 52. So 51 zeros, a decimal place, 51 zeros before this 1. So they gave us our critical value and they also gave us our alpha level. So looking at both of those, chi-squared is 244, which is greater than our critical value of 6.251, or our p-value of 1.02 times 10 to the negative 52 is very much smaller than a 10% alpha level. So whichever one you look at, we end up rejecting our null hypothesis. So the data does not follow a normal distribution with a mean of 100 and a standard deviation of 10. So again, this one I gave you the expected frequencies because we haven't studied normal distributions yet, but after next chapter you'll be able to find these expected frequencies on your own. So here's another example. Hagar tosses 3 coins 200 times and makes notes of how many heads show up on each of the tosses. Her results are as follows, so here's her observed frequency. And she's interested in finding out whether her results follow a binomial distribution. So this is another distribution we'll talk about next chapter when there's only 2 outcomes, and performs a goodness of fit test at 5% significance level. Again, because we haven't studied a binomial distribution yet, I gave you your expected frequencies for the number of heads that would appear on 200 tosses. So given that, go ahead and answer questions A through C. Make sure that all your expected frequencies are over 5. Find your null and alternative hypotheses and your degrees of freedom, and then actually do your chi-squared goodness of fit test. So part A, all of our expected frequencies are significantly greater than 5, so we don't have to worry about combining any categories like we did on the last one. Part B, our null hypothesis, always, again, that it follows whatever given distribution. In this case, it satisfies or follows a binomial distribution. Our alternative hypothesis is that it doesn't follow a binomial distribution. And our degrees of freedom, there's 4 rows, and so therefore 4 minus 1 is 3. Just kind of eyeball test here. When you're looking at this, like, your observed frequencies are pretty close to your expected frequencies versus the previous example. You had one where your observed frequency was over 100 and your expected frequency was 30. So you can kind of get an idea of how close your observed frequency is versus your expected frequency, and that's what these tests are looking at. So then using your graphing calculator, you should find that your chi-squared value was 2.43 and your p-value, your probability value, was 0.489. So then whether you use the critical value that they give us or the alpha level that they give us, our chi-squared value was 2.43, which is less than 7.815, our critical value, or our p-value of 0.489 is greater than our threshold value of 0.05. So either way, whichever way you look at it, we do not reject our null hypothesis, so therefore we are going to say that it does follow a binomial distribution. So this has been the chi-squared goodness of fit test, which is comparing one variable to a specific type of distribution, as opposed to the chi-squared test for independence, which is looking at 2 different variables and deciding whether or not they're independent from each other.